Hey students, welcome to Video 6d. So in this video we're going to take tooling forces that we calculated and then we're going to figure out what does that mean? What does that matter? And so there are some principles here that we can understand. If I have a block and I put it onto the end of a pin, if I'm using a locator pin, and I put it onto the end and I press with a certain amount of force, we should be able to figure out what the pressure is right at that interface. And what we're looking for is if the pressure gets to be too high, then we will actually deform the part, right? If we exceed the shear stress in the part, we will deform the part and we'll permanently have a little indentation in the part. And that can be really bad because if we press down and we indent the part, then we're not going to make our features at the correct height on the part because the whole part will have shifted lower in the fixture. Also, when we think about this, it's pretty clear that if I am pressing this block onto the end of a cylindrical locator like that onto a flat surface, the amount of pressure generated for that would be different than if I press it along this line contact on the side of the cylinder, and that would be different than if I press it on the end of a sphere. Now, one of those is easy to calculate, so just the two flats together is relatively easy to calculate what that stress would be because it's just force divided by the area, which is the area of the end, the cross-sectional area of the end of this dowel pin. But the others become much harder to calculate because if you think of this or you think of the sphere, as I push down on it, there's going to be a little bit of deflection that's elastic, right? And that elastic deflection, I don't actually mind if it, I may not mind if it deflects a little bit elastically. I have to know how much it is to know where the part is in the fixture, but when I take it off, that's going to recover and I'm not going to leave a dent in the end of my part. And so, but the calculation is really hard though, because as I press down, when it first touches on the end of a sphere, the contact is just a single point, so the pressure is enormous. But what happens, of course, is that we're going to deflect either the part or the locator, spherical locator, and pretty soon our contact is going to be a little bit of that hemispherical section. It'll be round in cross section and a little bit of the sphere. And there will be some point where it levels out, you know, to how hard I'm pushing down. And if that's in the elastic region, that's okay. If it is in the plastic region and it dented our part, then it's probably not okay. But the further we push it down, the larger that area gets, and so the whole thing is really complicated. It's very hard to figure out, and so on your own it is. And so there is a set of tables, and this is called Rourke's Formulas for Stress and Strain. It used to be the best book that you could give somebody as a graduation gift when somebody was going to go off to be a new engineer. It's a really dry book. There is just hundreds and hundreds of tables of stress and strain in it, and you can figure out all kinds of really cool ways to calculate stress and strain. Now it's online, so it's not such a good gift anymore, and that makes it harder when people graduate. But anyway, so let's look at Rourke's formulas for stress and strain and see how we would use it in this instance. Okay. So here we have the formulas for taking a sphere and putting some load P on the sphere. The sphere has diameter of D, and it will indent the surface, and the diameter of the radius, the diameter of the indent section will be 2A. Now remember, this could be elastic or it could be plastic. It will switch over some way through. So there are special cases for this, and so the first special case is a sphere on a flat. Second special case is a sphere pushing on a sphere, and the third is a sphere pushing on the inside of another sphere. So this is like a ball and socket joint. And these give you this value KD that you need to know on some of these different, on some of these calculations. So we're going to do a sphere on a flat. That's the most common thing that we'll be doing, is having a hemispherical locator, and then our part will be flat on that surface. So for that, for the KD, we use the diameter of the sphere. Okay, so how do we go about this process? If our sphere and our part are made of different materials, then we can use this formula right here to evaluate an equivalent Poisson's ratio. If both of our materials have similar yield strengths and similar Poisson's ratios, then we can use a simplified set of calculations down here. And what we are solving for when we do this is two things. We're going to solve for, this is the elasticity, or the stress, the maximum stress that is achieved when you put the load on the sphere. And so sigma C max is 0.918 times the cube root of the load divided by this value of KD squared, which is the diameter, times C sub E, this equivalent Poisson's ratio, and Young's modulus all tied up together. And when we do that, we will get this value for this maximum compressive stress. And then we take that maximum compressive stress. If we were doing it in a case where the E's were equal and the Poisson's ratios were equal, so if you have two steels, this will be really close. It's not actually always a bad assumption with aluminum either, though sometimes the, depending on what aluminum you're using, the Young's modulus can be quite different. So anyway, if you had this special case, then you would use this equation instead. And so we come out with this maximum compressive strength, and then we use this formula right here, and we multiply that maximum compressive strength times 1/3, and that gives us the maximum shear stress. I'm sorry, this is compressive stress, not strength. And so this gives us the maximum shear stress that we would that would occur in our material. So once we get this number, then we can look for the shear strength of the material that we're using, and we can compare it. If the shear strength of the material we're using is higher than this value, then the part will not be indented, and it will only be elastic compression that happens. If the shear strength of the material is lower than this maximum shear stress, then we will have to do something about that, or we will indent the material. Remember, when we start this also, we're going to have factors of safety in this value of P to make sure that we don't accidentally overload this and dent the material when we calculated that we weren't going to indent it. Well, what could we do if we want to make our shear stress value smaller? Okay, well, things that we could do, we could decrease the load. So we could figure out a way to decrease the load on our part. Usually we can't really do that. That would mean cutting more slowly. It would mean taking a shallower depth of cut. And those are all possibilities, but that's also not the fastest way to make a change here. A much faster way to make a change, because of the square here, is to increase the diameter of the sphere. And so one thing that we'll end up with is really big numbers for the diameters of the sphere. And so we can end up with numbers like 1 meter diameter for a sphere. And that's okay, because we don't have to use a sphere that is 1 meter in diameter we can take the end of a pen and just grind a little tiny portion of a sphere on there that has a 1 meter radius. It's going to appear almost flat, but it's going to have a little bit of a radius to it. The other thing that we could do is we could go and change this ratio by decreasing the, changing the yield strength of our materials to see if we can change this value of CE. The other way that you work this problem is sort of the inverse. You get the shear strength of the material, you calculate the maximum compressive stress that you can have from the maximum compressive stress, put it into this equation with the known load. That will give you a value for K sub d squared, which gives you a value for the diameter. And this will tell you the diameter has to be at least this big. And so you can run them backwards. Well, what if we don't have a spherical locator? What if we have a cylindrical locator? Well, there's a page for that too. And so this is the page for the cylindrical locator. Similar to the other one, you can do cylinder on a cylinder, cylinder on a flat. You can do a cylinder inside a cylindrical cut, and then crossed cylinders. So this is cylinders that have their long axes at orthogonal angles to each other. This is a really bad case. Don't ever set this up if you can help it. The deflection is just massive in there because you have line contact hitting line contact. So that ends up as being essentially a point, or it becomes a little tiny X and then becomes a little tiny sphere, but massive loads in this case. So what we're most often going to get here is something like a cylinder lying on its side on a flat, and then we would calculate this value for the maximum compressive strength. If we knew that the Young's modulus were similar and the Poisson's ratios were similar, we would use this instead, and then use this calculation to get from the maximum compressive strength stress to the shear stress. Okay, some warnings. Folks often like to try to do something with this value of B, and that is not a really good thing to work with. So try to stay away from doing much with that calculation of B. It can be interesting information, but it does not really help you, and it's not like you can say, oh, I'm going to specify that B is this value. That's not the way that we use these tables. Also, on the previous table, folks often want to do something with A, and they think that A is the amount that they're moving down or something, and that doesn't work at all either. Okay, so in class, we are going to do some calculations, and we're going to see what size locators we would have to use to not dent parts when we were doing different kinds of loading. All right, see you in class.